Hello there, calculus fans. I'm making a video here because my nephew asked me a question about solving this particular system of equations on the left here. But my real goal is to talk about just how we solve in general and some of the challenges that I've seen face students in my 20 years of teaching. And in particular, I've seen these three words, set them equal, lead to many student errors. The words themselves are not bad, but I think students misunderstand the idea of what we're trying to do when we're solving or finding intersections. So I'll do a few basic examples, and then I'll do other ones I could think of from my classes. So sometimes we have to solve to find the intersection of those two curves. Sometimes we have to solve to find the intersection of those two curves. And then I thought I would finish with something more exciting. I'll show you some 3D pictures, the intersection of two planes, the intersection of two curves in 3D, the intersection of two surfaces. And so this will tie in with some of my 3D images, because that's actually the class where I see these errors the most. Because as things get more complicated, students start to rely on the words set them equal. And that's when we get into trouble. Okay, so first, let's solve this one. We'll start with the one that my nephew asked me. And so what I said to him first is, your goal at the end of a problem like this, you're intersecting two lines. You don't want to use any words to guide you, not set them equal, not really anything else. You just need to know at the end you're going to have two numbers, x equals something and y equals something. And whatever they are, you're going to make sure they work in both these. You should think of equations as conditions. This is condition 1. This is condition 2. When you say you want to find the intersection, you want the numbers to work in both. That's an overarching thing. And so what I like about solving equations is I can always know if I'm right, especially when you're just finding numbers. So to me, it never makes sense for a student to submit a wrong answer. It makes sense for them to say, my answer doesn't work, I don't know why. But it never makes sense to submit a wrong answer, because you can check, and you can very quickly check. So sometimes I have students try to guess. I'm like, well, what if this was 0 and this was 6? Yay, it works. But then you go over here and you go 0, 6, boo, it doesn't work. So then you guess again, and you guess again, and you guess again, and you guess again until you find something. That's one approach to solving. It's not my favorite. What I tell students that always works is, sometimes I jokingly call it the take it and shove it method. It's really substitution, but it goes to the goal. The goal is not ever to set things equal. The goal is to start with whatever number of equations you have and reduce the number of variables. So I have two equations with two variables. In math, we like to say two equations with two unknowns, and we want to get down to one equation with one unknown. So if you do any sorts of combining, and the word I prefer to use is combine, we're trying to combine conditions. That's really what's happening. We're not trying to set anything equal necessarily. We're just trying to combine conditions. We have conditions for what it means to be on one line. We have conditions for what it means to be on the other line. We can easily find numbers that work on one or the other, but we'd like to find ones that work in both. We need to combine them. So how do we combine? The take it and shove it method says pick one of the equations. It doesn't matter which one. This is something that always works, and then I'll talk about maybe in this particular case there's sometimes faster ways. But you just grab one equation and solve for one variable. And I typically tell students to solve for the one that's easiest to solve for. And I know what I'm doing is not the fastest way, but I want to illustrate the take it and shove it method. Some students are taught to solve both and then set them equal, which is not wrong, but is a huge waste of time. Because if you already have this x, and now you know a condition for what x has to be, and your goal is to get it to one variable, then you're already there. You take this and you shove it in here. The moment you do that, you have reached your goal, which is to reduce the equation. Now, I'm not saying I did that in the cleanest way. Once we understand the idea, then the question shifts to, what is the cleanest way to do this? But the moment I get here, I tell students, I know that I have finished the problem. I'm not afraid of one equation with one variable. I know some students are. But my goal just becomes, this is success. I went from 2 equations with 2 variables to 1 equation with 1 variable, and now I can solve. So I would do 7 times 18, whatever in the world that is, minus 21y plus 3y, and you would just keep going till you solve. I tell students, I'm not afraid of this sorts of algebra. I like it. This would be negative 18. I move it over, it's going to be 18y. Well, I got lucky. Divide everything by 18, and I get y is 7. Now, the second question I get the most is, where do I plug that in? And there's an easy answer to that. You plug this in everywhere. Everywhere, everywhere, everywhere. Your whole, if you understand the goal, which was to find numbers that work in both. And so it needs to work in both. So you should be able to plug it in anywhere. In fact, you should plug it in both of the places to make sure you're right. X is going to be 18 minus 21, which is negative 3. And here, if you did this, you're going to get 7x equals negative 21, which is negative 3. They both give me negative 3. I'm done. But I don't care how you do it. There needs to be a moment. You need to realize that this is the moment when we won the game. The moment we got it down to one variable, we won the game. We won the solving game. Okay, so let's go back and talk about other ways to combine. And this is where students get confused. They're like they taught something about set equal, and I'm going to show you what I'm worried about, because I have seen this many times, and students get mad at me. They're like, why can't I do this? It seems like it works, and they will fight with me on it. So what I see students do is they get both sides equal to 0. I mean, this is so prevalent. All my classes, even beyond calculus, I've seen this error, and they set this equal to this. Now, technically that's true. It is true that 0 equals 0. You can say 0 equals 0 whenever you gosh darn want. So this is not incorrect, but it is not working. Here we get lucky because the 3 y's cancel. But in general, you're not working towards your goal. The moment you're combined, one variable should be gone. Sometimes you get lucky this way, and so students start to think this is going to work. Okay, so I never do that, and so that's why I avoid the words set equal. So the other thing I see is I'll see students set this equal to this, which is even worse because it's completely incorrect. It's not valid. I see it a lot. Okay, so there is another way that many people that are watching this are wanting me to say this now, which is you just set them side by side. And you say, well, if these two things are equal, if you have something equal to something else, and another thing equal to something else, and you subtract side by side, they should be equal. Subtracting equal things from equal things should be equal. What does that do here? Well, the reason you would want to subtract is because you can see the 3y cancels, which is what makes this a nice, simple problem. Because you're going to get x minus 7x, which is negative 6x, equals 18. And that gives you x equals negative 3. And that's, to me, the clear winner of who can do it the fastest. But you can see it was the same goal. We won the game here when we turned it into one equation with one variable. Then we got negative 3, and then we plug in negative 3 everywhere, and we would have gotten y is 7. That's it. My nephew did have a follow-up question, which is how would he graph this? But the graphing part is easy. I always tell students, if you're going to graph a line, you might as well graph the intercepts because they're really easy to find. All you got to do is put a 0 here, and then you would say y has to be 6, and you put a 0 here, and x has to be 18. So you can really graph the lines extremely quickly. There's 6, there's 18, there's one line. 2 points is typically the fastest way to go when you're graphing something. And then the other line, same thing. When x is 0, y is 0. Uh-oh, I've ran out of points, but I do have another one. Negative 3, 7. There they intersect. So you can do it pretty darn fast, but that wasn't the thing. Okay, so I would like to move on to some other scenario. Let's get rid of this and grab another one. And as we do more and more, I think you'll understand why I'm worried about the word set them equal. Okay, so here's a situation that bothers students. They've got these two conditions. There's a parabola and a line. What bothers them is it doesn't look like a line. And so I would bet, if I could bet money, that more than 50% of my classes would take the second equation and write y equals 3x and then set them equal. And that's not wrong, but they're not actually setting them equal. They're using the take it and shove it method. They're taking this and shoving it in there. And that's perfectly fine, but it's kind of a waste of time. Because if you understand what you're doing, you would realize you can do the take it and shove it method immediately. And these are little things, but can lead to bigger problems down the road. So I would say it already has one equation by itself. Take it and shove it in there. And then the moment we're there, we have one. We win. We have it down to one equation with one variable. We win the game. So I want students to shift perspective to that. The moment you have many conditions, you want to reduce the number. You want to combine the conditions to reduce the number of variables. At this moment, then we want to factor. Now that's a separate story of best strategies for solving one variable equations, but that's a video for another day. This leads to two possibilities: x equals 0 or x equals 3. And then you go, where do I plug it in? You plug it in everywhere. So you're going to plug in a 0 here. You're going to plug in a 0 here, and you get y has to be 0. You're going to plug in a 3 here. You're going to plug in a 3 there. Try them both. You get y is 9. There are two intersections. And that should make sense. You've got the standard parabola. Ta-da. You have the line y equals 3x. D-D. 3, 9. It's easier to graph if you make noises. We got to be good at that, because you're going to be graphing all the time in calculus classes. So take it and shove it. Don't ever set them equal. Okay. Next, what do we got here? Here's another example of something that throws people off. This happens a lot as you get into higher level courses, where you have an equation that's arranged in a way you're uncomfortable with. It doesn't have y by itself. And so once again, if I was going to bet on it, if I handed this to a pre-calculus student, they would solve for y and then they would set them equal, which shows a misunderstanding of the goals. The goal is to get it to one variable with one equation. This actually is a parabola on its side. It looks something like this. A sad parabola on its side. And then we have a line, y equals 3x. You want to, whenever possible, practice trying to graph without a grapher. If you have to always get a graphing device to graph things like parabolas and lines, you're not going to do very well in a calculus course. So I'm expecting there are two solutions here and here. And I know what I need to do. I need to combine to get it down to one variable. So let's play that game. Can we combine? Well, have we solved for any of the variables? Yeah, x is by itself in the first equation, and y is by itself in the second. So you can take your pick here. It doesn't matter. You can free yourself to whatever looks easier. So I will show you both, even though it doesn't matter, and they both give me the correct answer, I suspect. I haven't solved this yet. I'm doing this on the fly. If you replace the y, you're going to have this. 10 minus 3x squared. And you're going to have to show me you know how to simplify that. If you go the other way and take and shove the x, you get y is equal to 3, 10 minus y squared. I don't know what's better. They both look good to me. If I don't know how to simplify this, then I guess this might not look good, but this is 9x squared. If I don't know how to simplify this, this doesn't look good, but this doesn't scare me either. You wouldn't do both. You would just pick one. Either way, we've won. We got it down to one variable. If you wanted to keep solving, let's say I move this to the other side. 9x squared minus x minus 10 is 0. That's a strategy for quadratics, but again, that's for another video of how you solve quadratics. But then we get a single quadratic formula. Negative b plus or minus square root b squared minus 4ac all over 2a. Unless, does it factor nicely? I didn't even look for factors. Boo on me. It must factor nicely. 9. Oh, shoot. I've already gone this far. Let's embarrass myself. So 1, 36, 360. 361. 2 times 9 is 18. I thought I'd pick nice numbers. But I know I've won. I know I just have to plug the numbers. 361 over 18. All right, let's show this one. Once you have those two numbers, you'd plug each one back in. Now, in this case, I'm solving for x because I chose that one, which maybe was a dumb choice. Y will be 3 times whatever x is. Let's see those two equations. I have them here. This and this. Why did I think it was going to hit a nice value? I thought it hit at 1. But I only had visually checked. This is I should prepare the videos. Is one of my answers 1? And at the end, this is really important, especially as things get messier. You definitely would want to check. Now, if I plug in a 1 there, I get a 3. If I plug in a 1 here, I get a 9. A 1 here. A 3 here. So 1 should have been one of my answers. So now let's see where I went awry. Well, I'm going to go back. Maybe the other answer is just not nice. Maybe that's my issue. But if 1 is an answer, then you can factor out a 1. Again, that's a story for another day, which means this must be 9x. And the other one must be 10. That gives me, yep, that's it. So the two answers are x equals 1 and x equals negative 10/9. I see the other one just wasn't very nice. You could plug the x back in and get y is 3. You could plug this x in and get y is negative 10 over 3. That's it. Negative 10 over 3 would be there. Yeah. Okay, so now let's move on to these other situations. I hope you're understanding now that the goal is to get rid of one of your variables. Hey calculus fans, interrupting my own video here. I'm going to break the video into 2 parts because it got a little long, but please watch on to the next part where I talk about how some of the same ideas can be used to work with things in 3D and some of the challenges that are the same and different, but mostly it's the same idea. And I'll use it to show you how I found can give you the intersection of, a cylinder and a plane and some other things. So we'll find this curve, but it's still the same idea of combining conditions. So watch on to that next video if you're interested, but wanted to keep this first one, shorten this first one a little bit. All right, thanks. Hope that you let me know if that helped you.